In all the examples we've looked at so far, it's been obvious which direction the reaction had to go, right? The examples I've set up so that at the beginning, there was only material on one side of the equation, right? And so we knew which side was getting the plus x's and which side was getting the minus x's when we set up our tables, all right? But we're talking about equilibrium reactions, right? Which means they're going in both directions. And so there's nothing that says that the point at which we initiate the reaction has to have things only on one side, okay? In this video, we're going to look at how to decide how a reaction has to move to get to equilibrium in the situation that it already has things on both sides of the equation, right? So if we come across a system and it's already got things on the reactant side and the product side, then how do we tell which way the reaction has to go to get to equilibrium? The answer is we calculate something that is known as the reaction quotient. We call that uppercase Q for that, right? The definition of it is here, and you'll notice it looks exactly like the definition of the equilibrium constant. The only difference is that we call it Q when we're not sure, when we don't know whether the system is at equilibrium, or when we know the system's not at equilibrium, all right? So here the concentrations could be any set of concentrations, all right? Think about the cases we've looked at so far, where we started off with things on the left-hand side, but not on the right-hand side. That would mean my C and D concentrations were 0. In that case, my Q value would just be 0, right? Because I'd have 0 on the top, and I'd have concentrations raised to powers on the bottom. That would give me 0, okay? We know that as time goes by, this ratio has to approach the value of the equilibrium constant, right? Because given a long enough time, when the system gets to equilibrium, then this Q has to become equal to K. And that's the secret to how we can use this to figure out which direction the reaction has to go. So if I have a system and I want to know which direction it wants to go to get to equilibrium, what I do is I calculate that Q value, and then I compare that value to the value of the equilibrium constant, all right? Think about what the form of these things is. It's always products. Product starts with a P, doesn't it? It's always products over reactants, right? Where that's everything's raised to powers and all that, but that's the general form of it, okay? So if Q is smaller than K, then that says we don't have enough products, right? That's the case we've been looking at when we said we started off with nothing being on the right-hand side of the equation, right? In that case, Q is equal to 0. 0 is always smaller than K because K is some positive number, okay? So in that case, in order to get Q to grow, we have to make more products, and that'll take away reactants, right? That'll grow the top of that fraction, shrink the bottom. That'll make the value of Q get bigger. Suppose, on the other hand, Q is bigger than K. That says we have too much product already, right? And in that case, the reaction will actually want to go from right to left, what we usually think of as being backwards, okay? Because it's an equilibrium system, both reactions are going in both directions all the time, right? So there's no longer anything special really about what we're still calling products and reactants, but it might be better if we called them the left side and the right side. All right. If Q is equal to K, then my system's already at equilibrium, and then there's going to be no net reaction from there. Right? So this is one more tool that lets us decide what should happen if we have a system where there's already things on both sides of the equation. We want to know what the progress to equilibrium should be from there. So here's an example we can set up to do this, okay? This is ammonia synthesis from nitrogen and hydrogen. This reaction is done on very, very large scales all around the world because ammonia is a precursor to all sorts of fertilizers and things, okay? And so what are we gonna do? We're gonna have a mole of nitrogen, 3 moles of hydrogen, half a mole of ammonia. They're all in a 50-liter vessel at 400 degrees C. It says at that temperature, the equilibrium constant equals 0.5. And our question is, what should happen? Which way will the reaction go to get to equilibrium? Will we make more ammonia, or will some of the ammonia have to revert to being nitrogen and hydrogen? And then I'll set up an equation that would let us, in principle, find the equilibrium concentrations. As we'll see when we get to that part, actually solving that equation is kind of rough in this case. Some of you may be able to anticipate why, just looking at the form of that equation. So here are my initial amounts, right? So the first thing I want to do is I want to find out which direction this reaction is going to go. So I'm going to calculate my Q. Q is equal to what? The ammonia concentration squared, the nitrogen concentration, and the hydrogen concentration cubed. I guess I should say I did pop one thing in there between slides, I guess. Here I had numbers of moles and I had them in 50 liters, right? So I divided the moles by the 50 liters. So for the nitrogen, for example, I had 1 mole in 50 liters, so I should get 0.02, right? And that's how I got those numbers that are up there, all right? If I put the numbers in here, this is 0.01, that's squared. This is 0.02 and 0.06 cubed. I do the arithmetic for that, and the notes sitting beside me say I get 23.1. All right. K, the equilibrium constant, is equal to 0.5, according to our previous slide, right? So here my Q is much bigger than my K. That says I have too much ammonia, right? So this reaction wants to go that way in order to get to equilibrium. Okay, so now I know how to put things together to get what I want. I think I have another slide that'll give me more room to write. Yeah, okay. Now I know that I want my reaction to be going from right to left. All right, that means the minus is going on this side now, and the pluses are going over here. I use the stoichiometric coefficients as the coefficients on my x's, and that gives me 0.02 plus x, 0.06 plus 3x, and 0.01 minus 2x. All right. This is the part where my problem said I was going to set up an equation to make this, to solve for the concentrations, and now we can begin to see why. My equilibrium constant, which is the ammonia squared, it's got the same form as it did when we called it Q, except now we're using the concentrations when the system is at equilibrium. So I'm going to take that bottom row because that's my equilibrium amounts. That's equal to 0.5 because that's the value of K. And it's also equal now to 0.01 minus 2x, and that's squared. Here is 0.02 plus x, that's the nitrogen. And here is 0.06 plus 3x. That one is cubed. Okay, that equation, you can tell, is going to be a little bit rough, right? Because on the bottom there, I'm going to have an x to the 4th term. And that means I've got quite a bit of work to do if I wanted to solve that. All right. I wouldn't ask you to have that equation and solve it because there's not a nice, simple analytical way to do that. I will tell you, if you're interested, that I put that equation into the Wolfram solving engine, and it gave me x equal to 0.0039. So if you're interested, we could take that. We could take that number if we wanted. We could put that in for x up there in the final concentrations and evaluate it and see that we should get something at least really close to 0.5. And so it's solvable, but it's just not easy. Okay. Notice this is another example of a problem where it would be a lot of work to solve for x, and then assuming that you had a problem that asked you for one of the final concentrations, x would not actually be the answer, right? Because all the concentrations can be found easily once we know x, but x is not actually any of the final concentrations, right? So that shows us how to approach the problem when there is material already on both sides of our equation. We add one step on the front end to use that reaction quotient, the Q idea, to decide which way the reaction is going to go, right? In this case, our initial amounts had excess ammonia. They had more ammonia than they should have, and so the reaction would actually run in what we think of as the backwards direction. That would mean if we really wanted to have ammonia, we wouldn't want to let it react from there, right? It wouldn't get that far if we started with only nitrogen and hydrogen. Right? That gives you another tool in solving equilibrium problems, and so we have just a little bit more to look at. We will talk about something known as Le Chatelier's principle next, I believe.